There is a photograph of the universe being born. It is not a picture in the conventional sense, not an image captured by focusing light through a lens onto a sensor. It is something far more profound, an artifact of existence itself. This is a photograph painted with the residual heat of creation, an image whose light has been travelling towards us for 13.8 billion years. It is the universe's baby picture taken when it was a mere infant, just 380,000 years old. Before the first star had a chance to ignite its nuclear furnace, before the first galaxy began its majestic, swirling dance, before silence, before structure, before anything we would recognize as the cosmos, we know there was this light. An all-encompassing incandescent glow that filled every cubic centimetre of space with unimaginable energy. We call it the cosmic microwave background, the CMB. It is the oldest, most primordial light in existence, a fossilized echo of the Big Bang's ferocious generative power. For millennia, this light has been washing over the Earth, unseen, unfelt, unheard, a silent testament to our own fiery origins passing through our planet, through our homes, through our very bodies. It is a whisper from the dawn of time, carrying the most fundamental secrets of our universe, and we, a curious species on a small rocky world, have finally built the tools to not only hear that whisper, but to see the face of the one who speaks. For decades, our images of this primordial light have been blurry, like a treasured but faded family photograph. We could make out the general shapes, the broad strokes of our cosmic ancestry, but the fine details remained shrouded. The crucial storytelling textures were lost in a haze of cosmic distance and technological limitation. But that era is now over. What you are about to witness is a journey into that haze, a technological and scientific pilgrimage. We are about to pull back the cosmic veil with unprecedented clarity. Harnessing continent-spanning telescopes, supercomputers capable of simulating entire universes, and the collective genius of a generation of scientists, we have done something once thought impossible. We have taken that faint ancient afterglow and reconstructed it, rendered it in breathtaking, astonishing 8K resolution. This is not merely an upgrade in picture quality, it is a quantum leap in understanding. It is the difference between seeing a coastline from a distant ship and walking along its shores, examining every grain of sand. Every single pixel in this new atlas of creation is a data point of immense significance, each subtle variation in colour representing a temperature difference of mere millionths of a degree is a clue, a signpost pointing back to the first trillionth of a second of the universe's existence. This is the story of that achievement. It is the story of how we are using this remastered symphony of creation to answer the deepest questions we have ever dared to ask. Where did the great cosmic web of galaxies come from? What is the true nature of the dark matter that sculpts the universe with its invisible gravity? What is the mysterious dark energy that is accelerating our cosmic expansion, pushing everything apart towards a cold and lonely future? The answers, we believe, are imprinted in this light. They are encoded in the subtle patterns and textures of the universe's first moments, a celestial blueprint that we can now finally read. To comprehend the magnitude of this image, you must first journey back with us. Not just thousands or millions, but billions of years, back to a time when the universe was not the cold, dark, and mostly empty place it is today. Imagine a state of existence so alien it defies all terrestrial analogy. The entire observable universe, all the matter and energy that would one day form trillions of galaxies, was compressed into a space smaller than a single atom. Then, in an instant of unimaginable violence and beauty, it began to expand. The Big Bang was not an explosion in space, it was the explosion of space itself. In its first moments, the universe was a seething, chaotic inferno of pure energy and fundamental particles. A perfect uniform plasma hotter than the core of any star that would ever come to exist. In this primordial soup light was a prisoner. Photons, the very particles of light, were immediately absorbed and re-emitted by a dense fog of charged electrons and protons. A single photon could travel no farther than a few microns before colliding with a particle, its journey cut short, its direction randomized. The entire cosmos was opaque, a celestial blowtorch glowing with a brilliance that had nowhere to go. If you could have existed in that early universe, you wouldn't have seen anything. You would have been inside the light itself, bathed in a uniform blinding furnace from every direction. There was no darkness, no shadow, no structure. Only this perfect, homogeneous, trapped radiation. For 380,000 years, this was the state of reality. A long, cosmic childhood spent in a luminous fog. During this time, however, the universe was constantly expanding and, as a consequence, cooling. The frantic dance of particles began to slow. Eventually, the cosmos reached a critical transformative threshold, a temperature of about 3,000 degrees Kelvin. At this precise moment, the universe underwent its most profound change. It was cool enough for the agitated protons and electrons to finally bind together to form the first stable neutral atoms of hydrogen and helium. This event, which scientists call recombination, changed everything. Suddenly, the dense, charged fog that had imprisoned the light for millennia simply vanished. The primary obstacle for the photons was gone. The universe in a single glorious instant became transparent, and the light which had been trapped in a cosmic game of pinball since the dawn of time was finally set free. Released from its shackles, this primordial radiation flooded the newly transparent cosmos, travelling in straight lines, in every direction, unimpeded. This moment of liberation, this first light, is what we now see as the cosmic microwave background. It is a snapshot of the universe at the very instant it became see-through. But the journey of that light was just beginning. As it travelled through the eons, the universe itself continued to expand, stretching the very fabric of space-time along with it. And as space-time stretched, the light travelling through it was stretched as well. Imagine the sound of a siren. As it races towards you, the sound waves are compressed and the pitch is high. As it moves away, the waves are stretched and the pitch drops. The same thing happened to this primordial light. It began its journey as a brilliant, visible yellowish-white glow, not unlike the colour of a tungsten filament in an old light bulb. But as it traversed a universe that was growing larger and larger, its waves were stretched, shifting its colour down through the spectrum. From white-hot, it cooled to orange, then to a deep red. It passed through the infrared, becoming invisible to our eyes, and it kept stretching for billions of years across an ever-widening cosmic gulf. Its wavelength grew longer and longer, its energy ever more diffuse until it became what it is today. A faint, cold, ubiquitous sea of microwaves just 2.7 degrees above absolute zero. A whisper so faint it was mistaken for simple radio static for decades. The discovery of this whisper is a story of scientific serendipity of two radio astronomers in New Jersey. In 1964, Arno Penzias and Robert Wilson. They were building a new kind of antenna, and they were haunted by a persistent, annoying hum. No matter where they pointed their instrument, this low, steady hiss remained. They checked their equipment, they cleaned their antenna, they even chased away pigeons they thought might be the source of the noise. But the hum endured. It was coming from everywhere in the sky at all times, day or night, in every season. What they had stumbled upon entirely by accident was the echo of creation. The sound of the Big Bang, cooled and quieted by 13.8 billion years of cosmic expansion. That discovery transformed cosmology overnight, turning it from a field of philosophical speculation into a precise observational science. It was the single greatest piece of evidence for the Big Bang theory. The universe had a beginning, and this was its afterglow. Soon we learned to do more than just hear this hum. We learned to map it. Satellites like Kobe, the cosmic background explorer, gave us our first blurry view of this ancient light, confirming its near-perfect uniformity. It was almost exactly the same temperature in every direction we looked, just as the theories had predicted. Almost, but not quite. Kobe's instruments were just sensitive enough to detect minuscule, almost imperceptible variations. Tiny patches of the sky that were 100,000th of a degree, warmer or cooler than the average. These were not imperfections. They were revelations. They were the seeds of everything. Later missions like the WMAP satellite and the European Space Agency's Planck telescope would sharpen our view. With each new map, the blurry patches resolved into a more complex, intricate pattern of hot and cold spots. It was like moving from an impressionist painting to a detailed photograph. These maps became the bedrock of modern cosmology. By studying the size and distribution of these spots, we could measure the age of the universe with incredible precision. We could determine its composition, revealing a cosmos far stranger than we had ever imagined. A universe made of only 5% normal matter, the stuff of stars, planets, and people. The rest was a mysterious invisible substance we call dark matter, and an even more enigmatic force we call dark energy. These earlier maps were revolutionary. They gave us the fundamental recipe of the cosmos, but they still lack the resolution to answer our deepest questions. They showed us that the ingredients for a universe like ours existed, but they couldn't show us the fine details of the recipe. How exactly did these tiny temperature fluctuations orchestrate the grand cosmic ballet we see today? How did these infinitesimally small seeds of density grow into the gargantuan superclusters of galaxies that span hundreds of millions of light years? To understand that, we needed to see those seeds more clearly. We needed to zoom in, and that is the promise of this 8K reconstruction. It is an endeavour built on the shoulders of those previous missions, combining their data with new observations from ground-based telescopes in the driest, highest places on Earth. Places like the Atacama Desert in Chile, where the thin, stable atmosphere offers a crystal-clear window to the ancient universe. Instruments with thousands of detectors cooled to a fraction of a degree above absolute zero stare at the same patches of sky for years. Patiently, they collect the faint microwave photons that have completed their eon-long journey. This colossal stream of data is then fed into some of the world's most powerful supercomputers. Sophisticated algorithms work to filter out the noise to subtract the light from our own galaxy and distant galaxies that lies between us and our target. It is a process of cosmic archaeology, carefully digging through layers of celestial light to uncover the oldest, most pristine layer beneath. The result is what you are about to see. A map of the infant universe with such fidelity that it challenges the very limits of our understanding. Where the Planck satellite could see details down to about 10 arc-minutes of the sky, a patch about 1/3 the size of the full moon, this new map pushes that boundary significantly further. We can now see the imprints of phenomena that were previously only theoretical. We can hunt for the telltale signs of cosmic inflation, the hypothesized period of hyper-accelerated expansion in the first fraction of a second, which should have left subtle swirling patterns in the light. We can trace the intricate interactions between normal matter, dark matter, and radiation in the primordial plasma with exquisite precision. It's like having a perfect recording of a symphony's first chord. From that one chord with enough fidelity, you can infer the nature of every instrument in the orchestra, the exact dimensions of the concert hall, and even the skill of the conductor. In the same way, this one perfect image of the universe's first light allows us to infer everything that has happened since. It allows us to test our most fundamental theories about reality, to push them to their breaking point. Does Einstein's theory of general relativity hold up under the extreme conditions of the early universe? Are there new undiscovered particles that left their faint signature on this ancient light? Is the universe truly flat as our best theories suggest, or does it possess a subtle curvature that will determine its ultimate fate? These are the questions at stake. This is more than just a scientific treasure. It is our ultimate origin story. It connects us directly to the beginning of space and time. The slight overdensities you will see in this map, the slightly warmer, brighter regions, are the very places where gravity first took hold. They are the cosmic anchors around which matter began to clump. Over hundreds of millions of years, those clumps grew, pulling in more and more material until they became the first stars and galaxies. One of those galaxies would be our Milky Way. One of its stars would be our Sun. And from a cloud of dust orbiting that sun, the Earth would form. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in stars that owe their very existence to these tiny fluctuations in the universe's oldest light. We are the direct descendants of the patterns you are about to see. We are the universe made conscious looking back at our own birth. The journey to this moment has been one of humanity's greatest intellectual adventures, and now the final veil is about to be lifted. The message sent 13.8 billion years ago has arrived in stunning, unprecedented detail. Our task is to learn how to read it. The expedition into the heart of this ancient light into the very blueprint of our cosmos begins now. How does a story begin when its first word is light, not the flash of a camera, nor the flicker of a candle? This is a different kind of light, a phantom from a time before time as we know it, an echo from a bang that made no sound. For nearly 14 billion years it has been travelling a ghostly messenger from the very first moment of cosmic dawn, carrying within its ancient photons the secret history of everything. It is a story that begins not with a roar but with a whisper, a faint persistent hum that bathes the entire cosmos. To understand it, to see it, is to witness the birth of reality itself. But for millennia this primordial story was utterly invisible to us, shrouded in the deepest mysteries of space and time. Humanity has always sought its origin story. We have carved it into stone, painted it on cave walls, and woven it into the fabric of our oldest mythologies. We imagine titans and gods cosmic eggs, and primordial serpents all grappling in a void to bring forth the world we know. These were stories born of wonder attempts to answer the most fundamental question we can ask. Where did all of this come from? The 20th century, however, armed us with a new kind of storytelling. It gave us the language of mathematics and the tools of physics, allowing us to peer beyond myth and into the mechanics of creation. And what we began to uncover was a story far grander, far more violent and infinitely more strange than anything we had ever dared to imagine. The stage for this new cosmology was set by a single revolutionary mind. Albert Einstein, with his theory of general relativity, did not just redescribe gravity. He rewrote the very nature of the universe. He revealed that space and time are not a static, empty stage on which the cosmic drama unfolds. Instead, they are a dynamic, interwoven fabric, space-time, a substance that can be bent, warped, stretched, and compressed. Gravity, he showed, was nothing more than the curvature of this fabric caused by the presence of mass and energy. A planet orbiting a star is not being pulled by an invisible force. It is following the straightest possible path through curved space. His equations were elegant, powerful, and deeply unsettling, for they held a shocking implication. They predicted a universe that could not sit still. It had to be either expanding or contracting. This idea was so radical, so contrary to the prevailing wisdom of an eternal, unchanging cosmos, that even Einstein himself recoiled. He famously introduced a fudge factor into his own equations, the cosmological constant, to force his universe to be static. He would later call it his greatest blunder. But the universe is not obligated to conform to our expectations. The genie was out of the bottle, and others were brave enough to see where the mathematics truly led. A Belgian priest and physicist, Georges Lemaitre, was among the first. He imagined running the cosmic clock in reverse. If the universe was expanding now, then in the past it must have been smaller. Further back it must have been smaller still. Lemaitre took this logic to its ultimate mind-bending conclusion. He proposed that everything we see, every star, every galaxy, every atom in your body was once compressed into an infinitesimally small point, which he called the primeval atom. From this singular point, space and time themselves exploded into existence. It was a breathtaking, almost theological concept born from pure mathematics. For years, Lemaitre's idea remained on the fringes, a curious but unproven piece of cosmological speculation. Then, from a mountaintop in California, came the evidence. The astronomer Edwin Hubble, using the most powerful telescope of his day, was meticulously charting the cosmos. He was measuring the light from distant galaxies, and he discovered something astonishing. Almost without exception, the light from these galaxies was stretched. Its wavelength shifted towards the red end of the spectrum. This red shift was a telltale sign of the Doppler effect, the same phenomenon that makes an ambulance siren sound lower in pitch as it moves away from you. The galaxies were all racing away from us, but it was the pattern that held the key. The farther away a galaxy was, the faster it was receding. This was not a chaotic explosion of matter into a pre-existing void. This was something far more profound. The very fabric of space-time itself was expanding, carrying the galaxies along with it like raisins in a rising loaf of bread. Hubble's discovery provided the first observational proof Lemaitre had been right. Our universe had a beginning. The theory, later mockingly nicknamed the Big Bang by one of its detractors, was no longer a fringe idea. It was now the leading contender for our cosmic creation story. Yet a great theory needs more than just supporting evidence. It needs a unique testable prediction, a prophecy that, if fulfilled, would elevate it from a clever idea to an undeniable truth. For the Big Bang, that prophecy would be a whisper of light from the dawn of time. The physicist George Gamow, along with his students Ralph Alpha and Robert Herman, dove headfirst into the physics of the primeval atom. They imagined what that fledgling universe must have been like. It would have been a place of unimaginable temperature and density, a violent, chaotic furnace where matter as we know it could not exist. There were no atoms, no molecules, no stars or galaxies. There was only a searing, brilliant fog, a turbulent plasma of fundamental particles, protons, neutrons and electrons crashing into one another in a maelstrom of high-energy photons of light. In this primordial soup, the universe was completely opaque. A photon of light couldn't travel more than a few inches before being scattered by a free-flying charged particle. It was like being trapped inside the sun, a place of blinding light through which you could not see. For hundreds of thousands of years, the cosmos remained in this state, expanding and cooling, a cosmic fugue of light and matter bound together. But as the temperature dropped, a critical threshold was crossed. The universe became cool enough for protons and electrons, once too energetic to stay together, to finally combine, forming the first neutral atoms of hydrogen. This moment, known as recombination, changed everything. Suddenly, the fog lifted. With the free-flying, charged particles now locked away inside neutral atoms, the photons of the light were set free. For the very first time, light could travel unimpeded across the vastness of space. The universe in an instant became transparent. The light unleashed in that moment at the end of this cosmic dark age is what we now call the cosmic microwave background. It is the universe's very first baby picture snapped when it was just 380,000 years old. Gamow and his team made an extraordinary prediction. They calculated that this ancient light, this afterglow of creation, should not have vanished. It should still be here all around us, filling every corner of the cosmos, but it would not look like brilliant visible light. Over the ensuing 13.8 billion years of cosmic expansion, the waves of that primordial light would have been stretched, lengthened and cooled. Their immense energy would have dissipated, redshifting them all the way from the visible spectrum past infrared and into the microwave portion of the spectrum. The searing heat of the early universe would have cooled to a mere whisper, a faint background glow just a few degrees above the coldest possible temperature, absolute zero. It would be a perfect uniform radiation coming not from any star or galaxy, but from the fabric of space itself. It was the definitive smoking gun. Find this light, they argued, and you would have found the echo of the Big Bang. But their prediction, published in the late 1940s, was largely forgotten, a theoretical curiosity in a field that was still in its infancy. The technology to detect such a faint cosmic whisper didn't even exist. The universe, it seemed, was not yet ready to give up its oldest secret. That secret would finally be unearthed not by a team of cosmologists searching for the origins of the universe, but by two radio astronomers in Holmdel, New Jersey, who were just trying to get a clear signal. In 1964, Arno Penzias and Robert Wilson were working at Bell Labs using a massive horn-shaped antenna, originally designed for satellite communications. Their task was to survey radio signals from the Milky Way galaxy, and for that they needed to eliminate every possible source of interference. They calibrated their instrument with painstaking precision, accounting for radio broadcasts from Earth, and even the subtle heat radiated by the antenna itself. Yet after all their calculations, a persistent confounding noise remained. It was a faint, steady hiss, a low hum that was present no matter where they pointed their antenna. It was there at night. It was there during the day. It didn't change with the seasons. It came from every single direction in the sky with equal intensity. Their frustration grew. They checked the wiring. They rebuilt parts of the receiver. They ran diagnostic after diagnostic, convinced there was a malfunction, some mundane flaw in their equipment. Their most infamous effort involved a pair of pigeons that had taken up residence inside the giant horn. Penzias and Wilson wondered if the birds and what they left behind, what they delicately referred to as a white dielectric material, could be the source of this maddening anomalous heat signature. They captured the pigeons, drove them miles away, and released them only to find the birds had returned to their metallic home the next day. Exasperated, they resorted to a more permanent solution, thoroughly cleaning the antenna of all biological traces. And still the hiss remained, unwavering, unexplained. A ghostly hum from the cosmos itself. Completely at a loss, Penzias happened to mention their problem to a colleague who in turn had heard of a group of physicists just 30 miles away at Princeton University. This group, led by Robert Dick, was not trying to eliminate a strange noise. They were actively building an experiment to find one. Dick and his team had independently re-derived Gamo's earlier work, and had come to the same conclusion: the afterglow of the Big Bang should be detectable as a faint microwave hiss. They were on the cusp of searching for the very signal that Penzias and Wilson had been desperately trying to get rid of for months. The phone call that connected these two groups is now the stuff of legend. As Penzias described the inexplicable all-sky signal, the Princeton team realised what was happening. The story goes that after he hung up the phone, Dickie turned to his crestfallen colleagues and said, "Well, boys, we've been scooped." The two groups published their papers side by side in the Astrophysical Journal. One paper by Dick's team described the cosmological theory and the significance of what this background radiation would mean. The other, by Penzias and Wilson, was a masterpiece of scientific understatement titled simply "A Measurement of Excess Antenna Temperature at 4080 megacycles per second." That excess temperature, that annoying hiss, was no terrestrial noise. It was the voice of the infant universe. It was the faded warmth from the primal fire of creation. Penzias and Wilson had stumbled upon the smoking gun, earning them the Nobel Prize and cementing the Big Bang as the undisputed story of our cosmic origins. For a time, this discovery felt like a final answer. Humanity had finally captured the light from the beginning of time. We had the ultimate confirmation that our universe began in a hot, dense state and had been expanding and cooling ever since. The initial observations showed this cosmic microwave radiation to be almost perfectly uniform, a smooth, featureless glow across the entire sky. To an astonishing degree of precision, the temperature was the same in every direction we looked. This uniformity was in itself a powerful confirmation of the theory. It was exactly what you would expect from a universe that began as a thoroughly mixed, hot primordial soup. But as our ability to measure this light grew more and more precise, this perfect smoothness began to present a profound and deeply troubling new mystery, a paradox that threatened to unravel our entire understanding. Look around you. The universe is not smooth. It is magnificent in its complexity, its lumpiness, its structure. We live in a cosmos defined by towering galactic clusters and vast empty voids. We see intricate spiral galaxies, brilliant star-forming nebulae planets, moons and people. All of this magnificent structure, all of this intricate order had to come from somewhere. If the early universe was a perfectly uniform, featureless canvas, how did the first stroke get painted? How could a cosmos so flawlessly smooth at its birth give rise to the glorious textured reality we inhabit today? From that perfect, pristine glow, something had to curdle. Some seed, some tiny imperfection must have existed in that primordial light, serving as the gravitational anchor around which all cosmic structure would later coalesce. The greatest puzzle in cosmology was no longer finding the afterglow of creation. It was now a hunt for the flaws in its perfection. For a generation, this cosmic echo had presented us with an unnerving, almost philosophical paradox. It was a perfect, featureless glow, a thermal monotone humming at just 2.7 degrees above absolute zero, no matter where we aimed our instruments. This immaculate uniformity, this profound smoothness, was both the greatest confirmation of the Big Bang and its most confounding riddle. Because if the infant universe was a perfect undifferentiated sea of energy and matter, then how did weak gas happen? How could a cosmos born without any features, without any texture, possibly give rise to the glorious lumpy structure we inhabit today, where in that flawless embryonic state was the promise of a galaxy, the hint of a star, or the raw material for a planet you could one day call home? A perfectly smooth beginning should by all rights lead to a perfectly smooth and empty end. Gravity. The grand sculptor of the cosmos needs something to grab onto a slight concentration of mass, a placed just a little denser than its surroundings to begin its patient work of cosmic construction. Without those initial imperfections, those primordial seeds, the universe would have remained a thin, featureless, and eternally expanding hydrogen fog. There would be no cosmic web, no great walls of galaxies, no Milky Way, and certainly no one here to ask the question. The contradiction was so profound it bordered on a crisis. Theorists wrestling with the implications knew there had to be something more, a hidden layer of detail concealed within that ghostly hum. They calculated that for gravity to have had enough time to pull matter together into the structures we see, the primordial soup couldn't have been absolutely perfect. There must have been tiny, almost imperceptible variations in its density from one place to another. Regions infinitesimally denser than average would act as gravitational wells, cosmic potholes on the expanding fabric of space-time. Over millions of years, these regions would pull in more and more material, their gravitational influence growing their hunger insatiable. Conversely, regions slightly less dense would give up their matter, becoming the great voids that separate galactic superclusters. The entire majestic tapestry of the cosmos, it was theorized, was woven from these minuscule embryonic threads. The challenge, a monumental one, was to find them. We were searching for temperature variations of less than 1 part in 100,000. It was like trying to detect the heat from a single lit match on the surface of Pluto, while standing on Earth blinded by the glare of the sun. An entire generation of astronomers tried and failed their instruments earthbound, forever struggling against the noise of our own planet's atmosphere and the faint confounding glow of our galaxy. The whisper of creation was being drowned out by local chatter. To hear that whisper, we had to leave the cradle. We needed to rise above the atmospheric distortion to place a sentinel in the cold, clean void of space far from the thermal contamination of Earth. This ambitious dream took the form of a revolutionary spacecraft, an instrument of unprecedented sensitivity called the Cosmic Background Explorer, or COBE. Launched in 1989, COBE was less a telescope and more a cosmic thermometer of impossible precision, designed for one singular audacious purpose: to stare into the oldest light in existence and find the wrinkles that simply had to be there. Its primary instrument, the Differential Microwave Radiometer, or DMR, was a masterpiece of engineering. It wasn't a single detector, but a pair pointed at 2 different patches of sky 60 degrees apart. By constantly comparing the temperatures of these 2 widely separated regions, it could subtract the uniform background glow, cancelling out the overwhelming 2.7 Kelvin signal and allowing any minuscule residual differences to hopefully emerge. This differential method was ingenious, designed to filter out the deafening roar of the Big Bang itself to listen for the faintest of murmurs buried within. Another instrument, the Far Infrared Absolute Spectrophotometer, or FIRUS, was tasked with confirming the perfect blackbody spectrum of the radiation, a critical test of the Big Bang model itself. Guarding these sensitive electronics was a massive dewar filled with 650 litres of liquid helium, chilling the instruments to near absolute zero to prevent their own heat from contaminating the fragile cosmic signal. COBE was a high-stakes gamble, the culmination of decades of theoretical pleading and technological striving. If it found nothing, if the cosmic microwave background proved to be perfectly smooth, even at this incredible level of precision, then our entire understanding of cosmic evolution would be thrown into chaos. For years, the satellite orbited our planet in a silent, patient vigil. It spun gracefully like a gravitational gyroscope, its instruments shielded from the sun and Earth, methodically scanning the entire celestial sphere again and again. Down on Earth, a team of scientists, led by George Smoot and John Mather, began the painstaking, nerve-wracking process of assembling the data. Their task was Herculean. They weren't just looking for a faint signal, they were trying to extract it from a labyrinth of confounding noise. First, they had to model and subtract the microwave emissions from our own solar system, the faint heat of interplanetary dust. Then came the far greater challenge, the Milky Way. Our galaxy is a brilliant source of microwave light, a vast complex curtain of glowing gas dust and synchrotron radiation that stretches across the sky, obscuring the ancient light beyond. It was like trying to photograph a distant pale ghost through a vibrant, swirling fireworks display. The team had to meticulously map this galactic foreground at multiple frequencies, and then using complex computational algorithms peel it away from the data layer by layer. It was an act of cosmic archaeology digging through the recent geological strata of our own galaxy to unearth a fossil from the dawn of time. Months turned into years. The data accumulated, the maps grew sharper, the galactic foreground was slowly, carefully removed. Still, the underlying signal remained elusive, stubbornly, maddeningly uniform. The pressure mounted both from within the team and from a skeptical scientific community. Had they chased a phantom? Was the universe truly inexplicably perfect? Then slowly, agonizingly, a pattern began to emerge from the noise. As more and more data was averaged together, as the statistical uncertainty shrank, faint blotches began to appear on their all-sky map. They weren't instrumental artifacts. They weren't random noise. They moved with the sky, not with the satellite. At first, they were just tantalizing hints, ghostly apparitions in the data that could have been wishful thinking. The team was ruthlessly self-critical, checking and rechecking every aspect of their analysis, trying every conceivable method to make the signal disappear. They tried to break their own discovery to prove it was a mistake, but the pattern refused to vanish. It was real. It was undeniably, breathtakingly real. After 2 years of relentless scanning and forensic data analysis, they had their map. A celestial chart not of stars or galaxies, but of the universe as it was just 380,000 years after the Big Bang. And it was not smooth. The map glowed with colossal faint clouds of slightly warmer red and vast, cool oceans of slightly deeper blue. These were the temperature fluctuations, the anisotropies, the holy grail of cosmology. The differences were almost comically small, just a few dozen millionths of a degree separated the hottest spots from the coldest. Yet their implications were as vast as the cosmos itself. At a press conference in April of 1992, George Smoot, his voice trembling with the weight of the discovery, unveiled the image to the world. It was a mottled blue and red oval, an image that would become an icon of 20th century science. He famously declared that for the religious, it's like looking at the face of God. For cosmologists, it was something just as profound, the first direct evidence of the seeds of cosmic structure. These were the wrinkles in time. The warmer redder patches on the Code map represented regions of the primordial plasma that were infinitesimally denser than average. In these zones, matter had just begun to clump together, and the gravitational compression had heated the plasma by a microscopic amount. As a result, the light emitted from these regions was slightly more energetic, appearing to us today as a marginally higher temperature. The cooler bluer patches were the opposite, slightly underdense regions, the places from which matter was beginning to flee, creating what would become the colossal voids of intergalactic space. You're looking at the embryonic form of everything you have ever known. In that faint red blotch over there, that region just 30 millionths of a degree warmer than its neighbours, was a gravitational seed. A seed that over the next 13.8 billion years would patiently gather matter, its gravity growing stronger with every particle it captured. It would pull in vast clouds of hydrogen and helium, which would collapse to form the first stars. Those stars would live and die, forging heavier elements in their nuclear furnaces. They would form the first galaxies, which would then merge and collide, growing into sprawling island universes. One of those galaxies would be our Milky Way. And within a spiral arm of that galaxy, one particular cloud of gas and dust, enriched by the ashes of long-dead stars, would collapse to form a sun and its planets. And on one of those planets, life would emerge, evolve, and eventually build a satellite capable of looking back across the entire expanse of space and time to see the faint, ghostly outline of its own impossibly distant origins. Every galaxy, every star, every planet, every living being is a direct descendant of these faint primordial imperfections. We are here because the early universe was not perfect. Our existence is written in those wrinkles. The discovery was a watershed moment, a turning point that elevated cosmology from a field of often untestable speculation into a precision empirical science. The COBE results provided stunning vindication for one of the most audacious ideas in theoretical physics, the theory of cosmic inflation. Inflation proposed in the early 1980s suggested that in the very first fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated expansion, swelling from a subatomic size to cosmic proportions almost instantaneously. This incredible stretching would have magnified tiny quantum-scale fluctuations in the primordial energy field to astronomical sizes. These quantum jitters, once microscopic, became the macroscopic seeds of structure that COBE had finally seen. The properties of the wrinkles, their size, their distribution across the sky, matched the predictions of inflation with astonishing accuracy. It was a resounding triumph, a moment when the bizarre, almost mystical world of quantum mechanics was shown to be directly linked to the largest structures in the entire universe. Simultaneously, it was a death knell for older, simpler cosmological models that had no mechanism for creating these initial seeds. The game had changed forever. We were no longer just theorizing about the universe's origins, we were observing them. We held in our hands the cosmic blueprint. But like all great discoveries, the map from COBE raised as many new questions as it answered. While it proved the existence of the wrinkles, its vision was blurry, its resolution frustratingly low. The satellite's angular resolution was about 7 degrees across, meaning any feature smaller than 14 times the size of the full moon was completely smeared out. It was like looking at the blueprint for a grand cathedral with eyesight so poor you could only make out the shape of the building itself, but none of the intricate details of its arches, windows, or foundations. We could see the largest seeds, the ones that would grow into the mightiest superclusters of galaxies, but the smaller seeds, those that would give rise to individual galaxies like our own, were lost in the blur. To truly understand the recipe for the cosmos, to test the theory of inflation with the rigor it demanded, and to precisely measure the fundamental ingredients of our universe, we needed a sharper view. We needed to move beyond discovery and into the era of high-precision measurement. We needed to build new eyes instruments so powerful they could resolve not just the broad strokes of creation, but the fine, delicate details of its master plan. The quest had just begun, for hidden within the exact size and distribution of those wrinkles lay the secrets to the universe's age, its geometry, and its ultimate mysterious fate. That grainy image from COBE was a revolution, a ghost in the machine of the cosmos. It was the first time we'd seen the face of the nascent universe, a confirmation that the smooth, uniform cosmos we once imagined was a fiction. Hidden within that primordial fire were the whispers of creation, the infinitesimally small variations in temperature that would over billions of years blossom into the magnificent architecture of galaxies we see today. But COBE's vision, as groundbreaking as it was like viewing a masterpiece through frosted glass. It proved the seeds were there, but it could not read the genetic code they contained. The map was coarse, its resolution too low to decipher the intricate language written across the sky. We had found a Rosetta Stone, but the inscription was hopelessly blurred. What was the precise size of these primordial fluctuations? Was there a pattern, a hidden order to their distribution? And most importantly, what could that pattern tell us about the fundamental nature of reality itself, about the inventory of the universe and the destiny encoded in its first light? To answer these questions, we needed a new eye on the cosmos, an instrument of unprecedented stability and precision. We needed to leave the turbulent environment of Earth far behind. The result was a probe, an elegant feat of engineering launched in the summer of 2001, designed not merely to see the ancient light but to interrogate it. Its name was WMAP, the Wilkinson Microwave Anisotropy Probe. Its destination was not a planet nor a moon, but a point of profound gravitational stillness 1 million miles from Earth in the opposite direction of the Sun. This was the second Lagrange point, or L2, a cosmic oasis where the gravitational pull of the Sun and Earth balance, perfectly allowing a spacecraft to hover forever, keeping our planet and its star at its back. From this lonely, silent vantage point, shielded from the heat and radio noise of our world, WMAP could stare into the deep cold, its golden sensors pointed eternally toward the dawn of time. It wasn't just its location that made WMAP a revolution, it was how it saw the sky. Instead of measuring the absolute temperature of any one spot, which is fraught with instrumental error, WMAP's genius was in its differential radiometers. 2 telescopes pointed 141 degrees apart continuously scanned the heavens, measuring only the minuscule difference in temperature between 2 widely separated points. By spinning and precessing like a celestial top, it meticulously wove these differential measurements together, comparing every patch of the sky with every other patch over and over. This methodical process allowed it to cancel out its own noise and build pixel by pixel a map of the cosmic microwave background with 35 times the resolution of COBE. The first data release in 2003 was a watershed moment in the history of human thought. The blurry impressionistic painting from COBE was gone. In its place was a stunningly detailed portrait of vibrant tapestry of temperature variations. The sky was alive with a complex pattern of warmer red and cooler blue regions. For the first time, we could clearly see the structure within the primordial glow. There were spots of all sizes, but one particular size dominated the map, a characteristic scale of fluctuation that appeared again and again across the entire celestial sphere. This was the clue cosmologists had been dreaming of. To understand what WMAP had found, you have to imagine the early universe not as a silent void, but as a place of unimaginable violence and pressure, a roiling incandescent plasma. Before the atoms formed, this plasma was a cosmic battleground between the inward crush of gravity and the outward push of light pressure. This cosmic tug-of-war sent colossal waves of pressure sound waves sloshing through the primordial soup. Gravity would pull matter together into denser regions, making them hotter, but as the density and temperature increased, the trapped photons would push back with ferocious energy, causing the region to expand and cool. This cycle of compression and rarefaction of heating and cooling was a symphony of creation, playing out on a scale that dwarfs our imagination. Then, 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine. Atoms formed. Suddenly, the photons of light were set free from the plasma released to travel unimpeded across the cosmos for all time. That light, the CMB, carries a snapshot of the universe at the very moment it became transparent. It is a frozen image of those sound waves caught in mid-oscillation. The regions that were compressed and hot at that instant are the hot spots we see in the map. The regions that were rarefied and cool are the cold spots. What WMAP allowed us to do for the first time was to measure the precise characteristics of those ancient sounds. By analysing how many spots of each specific size appear on the map, scientists create a graph known as the power spectrum. This is perhaps the single most important plot in all of cosmology. It is the universe's unique fingerprint, its fundamental frequency, its cosmic DNA. And the most prominent feature on that graph is the first and largest peak, which corresponds to that dominant spot size WMAP saw so clearly across the sky. This peak represents the largest sound wave that had time to compress just once before the light was released. Its apparent size in our sky today holds a secret of monumental importance. Imagine drawing a triangle with you at one vertex and the two edges of one of these primordial hotspots as the other two. We know how large that spot was in the early universe, its physical size dictated by the speed of sound and the age of the cosmos at that time. We also know how far away it is, as it has taken light 13.8 billion years to reach us. With these two sides of the triangle, known simple geometry tells you what the angle at your vertex should be. The largest spots in the CMB should appear to be about 1 degree across in our sky. But this is only true if the fabric of space-time between us and that ancient light is perfectly flat. If space-time were positively curved like the surface of a sphere, it would act like a cosmic magnifying glass, and the spots would appear larger than 1 degree. If it were negatively curved like a saddle, it would minify them, and they would appear smaller. When the WMAP team measured the angular size of that first peak, the result was breathtaking. The spots were almost exactly 1 degree across. The implication was as profound as it was inescapable. On the largest scales, our universe is geometrically flat. This single measurement settled a debate that had raged for centuries. The universe is not closed, destined to collapse back on itself in a big crunch. Nor is it open, destined to expand so violently that it tears itself apart. It exists on a knife's edge, a perfect flat plane extending into infinity. But this flatness presented a new, even deeper puzzle. The gravitational pull of all the stars, gas dust, and even the mysterious dark matter we knew about was not nearly enough to create the required cosmic density to make the universe flat. There had to be something else, a missing energy component that accounted for over 2/3 of the entire cosmos. WMAP's data confirmed its existence with chilling certainty. We call it dark energy, a persistent anti-gravitational force woven into the vacuum of space itself, driving the accelerating expansion of the universe. And we have almost no idea what it is. The revelations from the WMAP power spectrum didn't stop there. Like a celestial symphony, the secrets were not just in the fundamental note, but in the overtones, the smaller peaks that followed the first. The second peak, a harmonic of the first, reveals the opposition between gravity and light pressure. Its height relative to the first peak acts as a cosmic scale, weighing the amount of ordinary baryonic matter, the stuff of atoms, stars, and ourselves. The answer was humbling. All of it, everything we have ever seen or touched, accounts for a mere 5% of the universe. The third peak then provided a measure for the invisible. Its characteristics told a story about the substance that provides the gravitational scaffolding for galaxies, the unseen puppeteer shaping cosmic structure, dark matter. BOSMAP's measurement was precise. 27% of the universe is composed of this enigmatic non-atomic substance. With one single elegant data set, DLMAP had given us the recipe for the cosmos. 5% ordinary matter, 27% dark matter, 68% dark energy. This became the standard model of cosmology, a triumphant theory that could now explain the universe from its first microseconds to the present day with stunning accuracy. It gave us a new definitive age for the universe, 13.77 billion years. For 9 years, WMAP scanned the heavens, refining its map, tightening the constraints, and building an unshakable foundation for our understanding of the cosmos. It transformed cosmology from a field of broad speculation into a precision science. And yet, as is always the way with deeper knowledge, came deeper questions. Our new standard model was built on two pillars of complete ignorance: dark matter and dark energy. And the very theory of inflation that so beautifully explained the origin of the CMB fluctuations predicted another far more subtle signal that WMAP was not sensitive enough to find. Science demanded a closer look. We needed to move from a high-resolution photograph to a quantum-level hologram. The call was answered by the European Space Agency with a machine of exquisite power and complexity. It was called Planck. Launched in 2009 and also sent to the Serene observation post at L2, Planck was the culmination of 2 decades of technological development. Where WMAP was a masterpiece of engineering, Planck was a work of art. Its detectors were cooled to within 1/10 of a degree of absolute zero, the coldest point in the known universe outside of a laboratory, making them almost supernaturally sensitive to the faint microwave glow. This incredible coldness reduced instrumental noise to a whisper, allowing Planck to detect temperature variations as small as 1/1,000,000th of a degree. It observed the sky in 9 different frequency bands compared to WMAP's 5. This wider spectral range was crucial for its primary mission, to perfectly distinguish the primordial CMB from the contaminating microwave fog of our own galaxy. By observing at many frequencies, astronomers could model the emissions from interstellar dust and gas, and then surgically subtract them from the map, leaving behind nothing but the pure, pristine light from the beginning of time. When Planck's final map was released, it felt like a veil had been lifted from the cosmos. The universe snapped into crystalline focus. The level of detail was simply breathtaking. The map had shown us the forest. Planck revealed every single leaf on every tree. The grand cosmological picture painted by WMAP was overwhelmingly confirmed. The universe was indeed flat. Its age was refined slightly to 13.8 billion years. And the cosmic recipe was tweaked but fundamentally unchanged. This confirmation was in itself one of the greatest successes in the history of science. 2 independent experiments using different technologies had arrived at the same startling description of reality. The standard model of cosmology was now established beyond any reasonable doubt. But with its surgical precision, Planck also began to reveal things that were unsettling. It saw subtle anomalies in the pattern of the ancient light things that shouldn't be there. A colossal cold spot. A region of the sky anomalously large and cool resisted simple explanation. There were faint alignments and asymmetries in the patterns on the larger scales that seemed to defy the core cosmological principle that the universe should look the same in all directions. Were these just statistical flukes, cosmic coincidences in the random throw of quantum dice? Or were they the first hints of new physics cracks appearing in our beautiful standard model, pointing toward a deeper, more complex reality, We had not yet imagined Planck's true power, however, lay in its ability to see a property of the ancient light the WMAP could only hint at its polarization. Light is a wave, and like a wave on a rope, it can oscillate in different directions. Polarization is simply the measurement of that wave's orientation. The primordial light of the CMB was polarized when it last scattered off electrons in the cooling plasma. Just as those electrons left an imprint of temperature, they also left an imprint of polarization. Planck was the first mission capable of mapping this faint polarization signal across the entire sky. It discovered a complex pattern of swirling-oriented light known as E-modes. These E-modes are generated by the exact same physics as the temperature anisotropies, the sloshing sound waves in the primordial fluid. Measuring them provided a completely independent way to test the entire cosmological model. It was like having a second independent witness to the birth of the universe. When the E-mode polarization data was analysed, it locked in the parameters of our universe with astonishing, unforgiving confidence. The numbers for dark matter, dark energy, and the density of atoms were no longer in dispute. They were now fundamental constants of our cosmos, measured and cross-checked. But there is another, far more elusive type of polarization predicted by our theories, a ghostly pattern 100 times fainter than the E-modes. They are called B-modes. Unlike E-modes, these swirling patterns cannot be created by simple sound waves. They are believed to be the unique telltale signature of something far more primordial. Gravitational waves, ripples in the fabric of space-time itself, generated not in the plasma 380,000 years after the Big Bang, but in the first trillionth of a second. These would be the gravitational echoes of cosmic inflation, the smoking gun of the Big Bang itself. Planck searched for this holy grail of cosmology with all of its unprecedented might. It scanned the skies, sifting through the galactic fog, straining to find that faint twisting signature. In the end, it found no definitive trace. But by not finding it, Planck did something just as important. It placed the most stringent limits yet on the nature of inflation, ruling out entire classes of theories and dramatically narrowing the search for those that remain. The journey from COBE to WMAP to Planck is a story of ever-increasing clarity. We have moved from a blurred shadow to an 8K ultra-high-definition reconstruction of our cosmic origins. We have taken the faint hum of creation and deciphered its symphony. We now know with a certainty that would have been considered science fiction just a generation ago the age composition and geometry of our universe. We hold a blueprint, a precise inventory of existence. Yet this remarkable clarity has not brought us closure. Instead, it has illuminated the edges of our knowledge, revealing the profound darkness that still lies beyond. The map is drawn, but its greatest treasures, the nature of the dark universe and the direct observational proof of our own violent beginning, remain tantalizingly out of reach, waiting for the next journey, the next discovery. The triumph was for a moment absolute. The cosmic microwave background revealed by the Planck satellite was no longer a fuzzy echo, but a breathtakingly sharp photograph of creation's dawn. For cosmologists, it was the equivalent of finding the original blueprints for the universe, a confirmation of a grand and elegant design. Every peak and valley and its temperature fluctuations seemed to sing in harmony with the predictions of our standard model of cosmology. This was it. The model which describes a universe composed of a mere 5% ordinary matter, 27% mysterious dark matter, and 68% of the even more enigmatic dark energy was seemingly vindicated. The data fit the theory with an almost unnerving precision, locking in the fundamental parameters of our cosmos with astonishing certainty. We had, it seemed, deciphered the universe's source code. The great questions appeared to be answered, the story of cosmic evolution written from its first fraction of a second to its far-flung future. But this is the treacherous beauty of science. When you build an instrument sensitive enough to capture a whisper from the beginning of time, you also build an instrument sensitive enough to hear the ghosts hiding in the silence. Absolute certainty is a mirage, and in the flawless face of the Planck data, tiny hair-raising imperfections began to surface. The new map, a masterpiece of scientific achievement, was paradoxically both a confirmation and a complication. Before we can even begin to understand the anomalies it hinted at, you must first appreciate the monumental task of its creation. For what Planck delivered to Earth was not a clean image. It was a deluge of raw, chaotic data, a cacophony of signals from which the fragile melody of the early universe had to be painstakingly extracted. The cosmic microwave background is incomprehensibly faint. Its whispers, having travelled for 13.8 billion years, arrive at our shores of space-time as the most delicate of signals, a thermal hum just 2.7 degrees above absolute zero. Imagine trying to listen for the flutter of a hummingbird's wings from across an ocean during a hurricane. That is the scale of the challenge. Our own Milky Way galaxy, a bustling metropolis of stars, gas and dust, screams in the very same microwave frequencies. It is a blinding fog of contamination that veils the ancient light beyond. To see the dawn, we first had to chart, understand, and then surgically remove our entire galaxy from the picture. This process, known as component separation, is one of the unsung epics of modern science. It is a high-stakes act of digital archaeology performed on a scale that beggars belief. The team had to contend with a menagerie of foreground signals, each with its own unique character and behaviour. First, there is the synchrotron radiation, a polarised shriek produced by electrons spiralling at nearly the speed of light around the galaxy's magnetic field lines. This is the glow of our galaxy's own powerful engine, a chaotic web of energy that must be meticulously mapped and subtracted. Then comes the thermal emission from vast frigid clouds of interstellar dust. These microscopic grains of carbon and silicate, colder than anything on Earth, radiate a faint heat that mimics the very signal we are hunting. To remove it, scientists had to model the distribution and temperature of countless dust clouds across the entire sky, essentially building a complete thermal model of the Milky Way just to throw it away. Another source of interference is the so-called free emission generated by ionized gas clouds, stellar nurseries, where new suns are being forged. Each of these foregrounds behaves differently at different frequencies, a complex puzzle that required Planck to observe the sky in 9 separate microwave and infrared bands. The data poured down from the satellite for over 4 years, accumulating into petabytes of information, a digital library larger than any ever assembled in human history. To process it, vast supercomputing clusters ran for months on end, executing algorithms of breathtaking complexity. These were not simple filters. They were sophisticated statistical engines designed to interrogate every single pixel of the sky at every frequency, and ask a deceptively simple question: what part of this light is from our neighbourhood, and what part is a relic from the Big Bang? It was like being handed a masterpiece painted over with layers of graffiti, and being asked to restore the original without ever having seen it. The international teams of scientists spread across continents worked in a state of sustained intense collaboration. They developed multiple independent processing pipelines, each using different assumptions and mathematical techniques. They would then compare their results, pixel by agonizing pixel, hunting for discrepancies. A variation might not be a feature of the early universe, but a subtle artifact of one team's algorithm, a ghost in the machine. Every decision was debated, every line of code scrutinized. The fear of being wrong, of accidentally inventing a feature of the cosmos that wasn't really there, was a constant motivating pressure. This process took years longer than the satellite's actual mission. It was a slow, deliberate, and often frustrating quest for a kind of computational perfection, and it was out of this crucible of extreme precision that the anomalies emerged. They were not loud, obvious errors, but quiet inconsistencies, things that just shouldn't be there, according to the elegant simplicity of the standard model. They were the statistical oddities you might dismiss in a lesser dataset, but in the crystalline clarity of Planck's map, they demanded attention. The most famous and perhaps the most unsettling is an immense patch of sky in the constellation Eridanus. It is a region far larger and far colder than it has any right to be. We call it, with a chilling simplicity, the cold spot. In the standard model, the hot and cold fluctuations in the cosmic microwave background should be random, like the static on an old television screen. There should be a predictable distribution of spot sizes. While you might expect to see some small variations, the cold spot is a gaping anomaly. It is a cosmic bruise, an area of such profound coldness that the odds of it occurring by pure chance are less than 1 in 1,000. In a map containing millions of random data points, a 1 in 1,000 event isn't impossible, but it is deeply suspicious. It makes you lean in closer. It makes you question everything. The initial reaction from the scientific community was one of profound skepticism. Surely it had to be an error. Perhaps it was a remnant of foreground contamination, a stubborn cloud of galactic dust that had evaded their meticulous cleaning procedures. Or maybe it was an instrumental artifact, a subtle flaw in one of Planck's sensitive detectors. Teams went back to the raw data, rerunning the component separation with different models trying to make the cold spot disappear. They reanalyzed the instrument's performance logs, searching for any glitch that correlated with observations of that patch of sky. But the cold spot stubbornly remained. It was real. It was there in the data from Planck's predecessor WMAP, though blurred and indistinct. Planck had simply brought it into sharp, undeniable focus. With the possibility of error-dwindling cosmologists were forced to confront its staggering implications. What could create such a vast cold imprint on the infant universe? One leading hypothesis is that the cold spot is not an intrinsic feature of the background radiation at all, but rather a shadow cast across it. Light from the CMB that has travelled through a particularly empty region of space, on its way to us, would lose energy appearing colder. This would require the existence of a supervoid, an immense bubble of cosmic emptiness hundreds of millions of light-years across standing between us and the ancient light. Searches for such a void have yielded ambiguous results. There seems to be a deficit of galaxies in that direction, but perhaps not one large or empty enough to fully explain the phenomenon. The more exotic explanations venture into the realm of science fiction, pushing the very boundaries of known physics. Some theorists have proposed that the cold spot is evidence of a cosmic texture, a kind of topological defect in the fabric of space-time, a remnant of a phase transition in the ultra-early universe. But the most mind-bending possibility, the one that inspires both awe and a deep sense of cosmic vertigo, is that the cold spot is the scar from a collision. It could be the observational proof that our universe is not alone. In this speculative but mathematically plausible scenario, our universe is just one bubble in a vast churning multiverse of other bubble universes, and 13.8 billion years ago our infant cosmos may have bumped into another. Such a collision would have sent shockwaves through our universe's primordial plasma, leaving behind a detectable circular bruise on the cosmic microwave background. The cold spot could be the first empirical evidence that we live in a far grander and far stranger cosmic reality than we ever dared to imagine. It is a tantalizing, almost frightening possibility born from a subtle chill in a map of the sky. Yet the cold spot was not the only spectre haunting the Planck data. Another more subtle but potentially even more profound discrepancy began to crystallize, one that threatened to unravel the very expansion history of the universe. This problem has become known as the Hubble tension. It is a conflict not within a single map, but between two fundamentally different ways of measuring the same cosmic number. The Hubble constant, the rate at which our universe is expanding today. Planck's data gives us one way to determine this number. By precisely measuring the size of the fluctuations in the early universe, the hot and cold spots scientists can use the standard model of cosmology as a kind of cosmic calculator. They know the physics of how that primordial plasma should have evolved. They can calculate how large those spots should appear to us today given 13.8 billion years of expansion. By comparing the predicted size with the observed size, they can infer the expansion rate with incredible precision. It is a beautiful piece of deductive reasoning, a prediction of the present based on a detailed photograph of the distant past. Planck's data run through this theoretical engine yielded a Hubble constant of about 67.4 kilometers per second per megaparsec. But there is another way to measure the expansion rate, a more direct method that relies on looking at the universe around us now. For decades, astronomers have been building what they call the cosmic distance ladder. They use certain types of stars, like Cepheid variables whose intrinsic brightness is known. By measuring how faint they appear, we can calculate how far away they are. By measuring the redshift of their host galaxies, we know how fast they are receding from us. This method, refined over decades and championed by teams using the Hubble Space Telescope and other powerful observatories, allows for a direct measurement of the universe's present-day expansion. And this is where the tension arises. The number derived from this direct local measurement is significantly different. It comes out to be around 73 kilometers per second per megaparsec. The two values disagree. At first, the discrepancy was small enough that it could have been a statistical fluke, a result of unaccounted for errors in one or both of the measurements. But as Planck's data became more precise, and as the measurements of the local universe became more accurate, the error bars on each value began to shrink, and they did not shrink to overlap, they shrank to exclude one another. This is a cosmologist's nightmare. It is as if you meticulously measured the foundations of a skyscraper to be a perfect square, while a second surveyor using equally precise laser instruments measured the roof and found it to be a perfect circle. Both measurements are exquisitely precise, and both cannot be right. Something about our understanding of the building itself, our fundamental model of the universe, must be wrong. The Hubble tension is not a flamboyant anomaly like the cold spot. It is a quiet mathematical crisis. It suggests a deep flaw in our cosmic story, a missing chapter between the era of the cosmic microwave background and the universe we see today. What could be the cause? Perhaps dark energy. The force driving cosmic acceleration is not a constant. Maybe its strength has changed over time in a way our standard model doesn't account for. Or perhaps there is a new undiscovered particle that filled the early universe, a form of dark radiation that would alter the expansion history in just the right way to resolve the tension. It could even be a hint that our understanding of gravity codified in Einstein's theory of general relativity is incomplete on the largest of scales. The glorious certainty that the Planck map initially seemed to offer had evaporated, replaced by a thrilling, unnerving sea of new questions. The very act of achieving unprecedented precision had revealed the cracks in our most successful theory. The standard model of cosmology, for all its power and elegance, was shown to be not the final word, but perhaps just a remarkably good approximation of a deeper, stranger reality. The quest to create an 8K reconstruction of this ancient light is therefore driven by more than just aesthetic curiosity. It is a desperate search for clues. By pushing the resolution even further, by enhancing the detail in these subtle anomalies, we hope to find the tells. We want to see if the cold spot has a finer structure that might hint at its origin. We want to refine the CMB's parameters to see if the Hubble tension sharpens or resolves. Every new pixel, every refined measurement is another page in this unfolding cosmic detective story. The perfect map had served its purpose. It had shown us the grand architecture of the cosmos. But now we are obsessed with its imperfections, for it is in the flaws, in the subtle deviations from expectation, that the next great revolution in our understanding of the universe likely lies hidden. We are no longer just admiring the blueprint. We are now searching for the architect's hidden notes scribbled in the margins, pointing the way toward a new and unknown physics. And so, the greatest treasure trove of cosmic information ever assembled lay waiting. Decades of meticulous observation, culminating in the unparalleled precision of the Planck satellite, had given us a deluge of raw data. Petabytes upon petabytes of faint whispered signals from the edge of time buried within a torrent of electromagnetic noise. It was a masterpiece, but a masterpiece shattered into a billion pieces and scattered across the static of the local universe. To the naked eye, it was chaos. A beautiful, tantalizing chaos, yes, but not yet the coherent story of creation we had spent generations searching for. The raw light from that primordial fireball had travelled for 13.8 billion years, only to be contaminated in the final milliseconds of its journey, veiled by the glowing dust of our own Milky Way, distorted by the glare of distant galaxies, and smeared by the very instruments we built to capture it. The challenge before us was monumental, a task of digital archaeology on a scale never before attempted. We had the faint echo of the Big Bang, but to truly hear its voice, to reconstruct its first word, we would need to build a machine capable of silencing the rest of the cosmos. This was a task far beyond human hands or minds. It required a new kind of cathedral for the modern age, a temple, built not of stone and glass but of silicon copper and cooling fluid. We turned to the leviathans of computation, the world's most powerful supercomputers. These are not merely faster versions of the device on your desk. They are sprawling, city-like architectures of pure processing power, consuming megawatts of electricity and thinking in quadrillions of calculations per second. Inside their humming server racks, we gathered the entirety of the Planck data, alongside the foundational work from COBE and DOE map, creating a digital ghost of the entire observable sky. This wasn't a matter of simply opening a file. It was an act of cosmic ingestion, feeding the beast an almost incomprehensible volume of information, every single photon ever captured from that ancient light. The goal was to forge what had never existed before, a single, unified, impossibly clean portrait of the infant universe. The first command given to this digital titan was one of subtraction. Imagine trying to record the sound of a single pin dropping in the middle of a raging hurricane. The hurricane is our own galaxy. Its swirling arms of gas, its incandescent nebulae, and its shroud of cold dust all shine brightly in the same microwave frequencies as the ancient light we seek. This galactic foreground is 1,000,000,000 times brighter, a deafening roar that completely overwhelms the primordial whisper. To solve this, scientists developed a suite of breathtakingly sophisticated algorithms, a form of celestial noise cancellation. The software had to learn the unique spectral signature of every conceivable contaminant. It learned to recognize the specific thermal glow of interstellar dust, distinguishing it from the black body spectrum of the cosmic microwave background. It identified the synchrotron radiation from electrons spiraling in the galaxy's magnetic fields. It tagged and isolated the glare from thousands of other radio sources in the distant universe. For years, the supercomputers churned. They ran countless simulations, creating model universes filled with every known type of foreground interference. They compared these models to the real data pixel by agonizing pixel across 9 different frequency bands. The algorithms were like a digital immune system, identifying and attacking anything that was not of the ancient universe. They performed a kind of cosmic peeling meticulously, lifting away layer after layer of contamination. First, the brightest, most obvious sources vanished. Then the diffuse, almost invisible curtains of galactic haze were identified through subtle, statistical variations and carefully excised. It was a process of relentless purification, a search for the authentic signal buried beneath a mountain of cosmic noise. With each passing cycle, with each layer of the modern universe stripped away, the faint mottled pattern of the past began to emerge like a fossil being delicately brushed clean from ancient stone. We were looking deeper past the stars, past the galaxies, past everything that has ever been to see the universe as it was. But cleaning the data was only the first step. The map we had was still a projection, a 2-dimensional photograph of a 3-dimensional event that surrounded us completely. To truly understand it, we needed to unwrap the sky. The tool for this is a form of higher mathematics known as spherical harmonics. Think of it as a cosmic symphony. Any complex sound can be broken down into a combination of simple, pure notes or frequencies. In the same way, the intricate pattern of hot and cold spots on the CMB can be broken down into a combination of fundamental shapes or angular scales on the sphere of the sky. These spherical harmonics are the pure notes of the universe's first song. The largest scales, the lowest notes, represent the broadest temperature variations stretching across the entire sky. The smaller scales, the higher, more intricate notes reveal the fine details, the tiny ripples on the surface of that primordial plasma. The supercomputers began this immense decomposition, transforming the cleaned map of temperatures into a power spectrum, a definitive cosmic fingerprint. This spectrum showed us precisely how much energy was present at each specific angular scale. It was the universe's genetic code written in the language of temperature and light. And it was here that the true act of reconstruction began. The data from Planck, as magnificent as it was, still had a finite resolution. There was a limit to the smallness of the details it could physically see. But the power spectrum, our cosmic blueprint, told us what should be there. It predicted the statistical nature of the fluctuations on scales even finer than what the satellite could resolve. Our understanding of physics, of how a fluid of plasma and light should behave under the influence of gravity and pressure, allowed us to do something extraordinary. We could now begin to intelligently fill in the gaps. This is the heart of the 8K reconstruction. It is not an artist's impression. It is not a guess. It is a scientifically rigorous act of computational inference. Using the flawless power spectrum as their guide, new algorithms began to work backwards. They took the slightly blurry, pixelated reality of the observed data and started to sharpen it, adding in the finer harmonics, the higher frequency notes that the physics told us must be present. Every new smaller pixel they generated was statistically consistent with the larger pattern surrounding it and with the overall cosmic symphony defined by the power spectrum. It was like having a low-resolution photograph of a face and using a perfect understanding of human anatomy to reconstruct the pores, the fine lines, the subtle textures that you know must exist. The computer was re-rendering the dawn of time not from imagination, but from the fundamental laws of the universe itself, as encoded in the light we'd already captured. It was resurrecting a level of detail that had been lost to the blurring effects of distance and instrumental limits. Slowly, painstakingly, over months of relentless computation, the new universe came into being. As the final processing cycles completed, the image resolved on the screen. And it was breathtaking. What had once been a mottled, slightly out of focus collection of blobs became a vast, intricate tapestry of staggering detail. For the first time, we could see the dawn of creation not as a blurry photograph, but as a high-definition vista. It is the single most important image in human history, the very seed of everything you see around you, now rendered with a clarity that our ancestors could never have dreamed of. You are looking at the universe at the moment of its birth as a physical system, 380,000 years after the Big Bang. Here in stunning 8K resolution is the frozen echo of creation's first roar. Those deep blue regions, infinitesimally colder than average, are the seeds of cosmic structure. These are the patches of the universe that were by a mere 1 part in 100,000 denser than their surroundings. And the fiery orange and red zones are their counterparts, the slightly less dense, slightly hotter regions. This is it. This is the source code of reality. Every star, every planet, every galaxy, every great supercluster, and even the vast empty voids between them, all owe their existence to these minuscule quantum fluctuations, now revealed in exquisite detail. You are not looking at a picture of objects. You are looking at a picture of gravity itself. These cold spots are the primordial gravity wells, the cosmic anchors, that would begin the slow patient process of assembling matter over the next 13 billion years. To prove this connection, to bridge the unfathomable gap between then and now, the scientists performed one final spectacular act of computation. They took this 8K map, this precise set of initial conditions, and fed it into an entirely new kind of simulation, a simulation of cosmic evolution. They pressed a metaphorical play button, and on the screen time began to flow. The simulation was governed by only the known laws of physics, gravity, the expansion of space, and the behavior of dark matter and dark energy. For the first few million years, not much appeared to happen. The map of fluctuations remained gently stretching as space itself expanded, but the subtle power of gravity was at work. In the cold, dense regions, the invisible scaffolding of dark matter began to clump together. The pull was weak, almost imperceptible, but it was relentless. As the simulation accelerated through hundreds of millions of years, we witnessed a miracle. Those initial cold spots, those anchors in the fabric of space-time, began to pull in the surrounding hydrogen and helium gas. The first filaments of the cosmic web started to form delicate glowing threads, stretching between the densest nodes. The red underdense regions, meanwhile, emptied out their matter, siphoned away to feed the growing structures becoming the great cosmic voids. The simulation raced forward 1 billion years, ticking by every second. The filaments grew brighter and more massive. At their intersections, where the pull of gravity was strongest, the gas collapsed under its own weight, igniting in a blaze of nuclear fusion. The first stars and then the first galaxies were born. And they were born in exactly the places predicted by that ancient map. The simulation continued to run through 5 billion years, 10 billion, all the way to the present day. What emerged was a universe that was statistically indistinguishable from the one we see around us through our telescopes. A vast interconnected web of galaxy clusters and superclusters separated by immense voids of nearly empty space. The link was undeniable. The 8K reconstruction was not just a picture of the past, it was a confirmed blueprint for the present. We had successfully reverse-engineered the cosmos, tracing the lineage of the Milky Way, of our neighbouring Andromeda, of the Great Virgo supercluster, all the way back to their specific individual seeds in that first flash of light. The pattern of galaxies across the heavens is not random. It is a direct gravitational echo of the pattern of quantum noise that existed at the beginning of time. And hidden within this pattern, within the precise distribution of those hot and cold spots, are even deeper secrets. The 8K map is a tool for testing the most extreme physics imaginable. It allows us to scrutinize the theory of cosmic inflation, that hypothetical moment of hyper-accelerated expansion in the very first trillionth of a second. The specific statistical properties of the fluctuations, their near-perfect scale invariance, their Gaussian distribution, are powerful confirmations of inflation's core predictions. It's like finding the precise shockwave pattern in the air after an explosion and being able to reconstruct the nature of the explosive itself. By studying this light, we are studying the physics of the Big Bang's immediate aftermath. We are probing energies and conditions that we could never hope to replicate on Earth, using the entire observable universe as our laboratory. This reconstructed portrait is our witness, a silent, unblinking eye that saw the forces that forged all of space-time, matter and energy. It is the answer to a question we barely knew how to ask. Yet like all great discoveries, this ultimate map does not close the book. It opens 1,000 new chapters. Its staggering precision has brought subtle anomalies and strange alignments into sharp focus features in the data that do not perfectly match our standard model of cosmology. Are these mere statistical flukes the cosmic equivalent of seeing a face in the clouds, or are they the first hints of a new undiscovered physics, a crack in our understanding of the universe? This image, this gift from the dawn of time, has provided us with the most profound answers in the history of science, but it has also handed us a new set of mysteries written in a language we have yet to decipher. It is the final page of one story and the magnificent, tantalizing first page of the next. And so we are left here in the quiet afterglow of creation. You have now gazed upon the face of the infant universe, a moment frozen in time, resurrected from an abyss of 13.8 billion years, and rendered with a fidelity we could once only dream of. This image, this breathtaking canvas of cosmic birth, is the destination of a journey that began not with a grand design, but with an annoying, inexplicable whisper. A persistent hiss from the heavens that refused to be silenced, a cosmic static that two young radio astronomers in 1964 tried everything to eliminate, even scrubbing their horn antenna clean of pigeon droppings. Little did Arno Penzias and Robert Wilson know they weren't cleaning away noise. They were listening to the residual echo of the Big Bang itself. That faint, omnipresent hum was the sound of a universe being born, a thermal ghost story told across the entire sky. From that moment of accidental profound discovery, our quest to understand this relic radiation became one of the greatest detective stories in the history of science, a multi-generational effort to bring a ghost into focus. The first crude temperature readings gave way to humanity's first true glimpse, delivered by the Cosmic Background Explorer, or COBE, in the early 90s. Its map was blurry, a mottled pattern of colour blotches, yet within that impressionistic view was a scientific revolution. It confirmed the whisper was real, that it had a thermal spectrum of near-perfect blackbody radiation, and most crucially it revealed the first hints of texture. The afterglow wasn't perfectly smooth. There were tiny, almost imperceptible variations in temperature ripples on the surface of a primordial ocean, 1 part in 100,000. Those faint smudges were everything. They were the first structures in existence, the gravitational seeds from which all future complexity would grow. COBE gave us the question, but the answer was still shrouded in mist. Then came the next great leap in our cosmic vision. The Wilkinson Microwave Anisotropy Probe, WMAP, launched at the dawn of a new millennium, stared at this ancient light for nearly a decade, its vision far sharper than COBE's. The blurry blotches resolved into a finer, more intricate pattern. It was like moving from a distant glimpse of a mountain range to seeing the individual peaks and valleys. WMAP's data was so precise, it transformed cosmology from a field of broad theories into a discipline of precision measurement. From that intricate tapestry of hot and cold spots, we could finally read the universe's vital statistics. We pinned down its age with astonishing accuracy. We measured its geometry, confirming that space on the larger scales is flat. And most humbling of all, we took a definitive cosmic inventory. The results were staggering, a complete reordering of our place in existence. All the stars you can see, all the galaxies we have ever photographed, all of us, everything made of atoms amounted to less than 5% of the cosmic budget. The rest was a profound mystery composed of an invisible gravitational scaffolding we call dark matter, and a yet more enigmatic, repulsive force, dark energy, that is relentlessly pushing the cosmos apart. WMAP didn't just take a picture, it revealed the soul of the universe and found it to be overwhelmingly, fundamentally alien to our everyday experience. Following WMAP, the European Space Agency's Planck satellite pushed the boundaries of perception to their absolute technological limit. Its instruments were so sensitive, cooled to 1/10 of a degree above absolute zero, that they could detect temperature variations of a few millionths of a degree. If WMAP showed us the peaks and valleys, Planck revealed the individual rocks and grains of sand. The cosmic symphony once heard as a single faint tone was now resolved into its full magnificent orchestration. Planck's data became the new gold standard, the bedrock of modern cosmology, a map so detailed it challenged our most advanced theories of the universe's first moments. And it is from this exquisite data, this wealth of information harvested by Planck and refined by decades of observation from Earth-based telescopes in the high Atacama Desert, that the image you have just seen was born. The culmination of a century of theory and a half-century of exploration painstakingly processed through supercomputers stitch by stitch, pixel by pixel, transforming a map of microwaves into a vision our eyes can finally appreciate. This is what it means to see the oldest light. It is the final triumphant answer to the question that began with that inexplicable hiss. To call this image a mere picture is to profoundly misunderstand its significance. It is the universe's ultimate Rosetta Stone, a cosmic blueprint containing the genetic code for everything that would ever exist. Those minuscule fluctuations in temperature and density captured here in stunning relief are the most important features in the cosmos. They are the slight imperfections in an otherwise impossibly uniform primordial soup. In the breathless furnace of the early universe, these regions, infinitesimally denser than their surroundings, possessed a slightly stronger gravitational pull. Over the first few 100 million years, as the cosmos expanded and cooled in darkness, that tiny gravitational advantage became decisive. These denser patches acted as cosmic anchors, patiently and inexorably pulling in matter from the less dense regions around them. Gravity, the silent, relentless architect of the cosmos, began its work. Gas and dark matter swirling in the blackness fell into these gravitational wells, accumulating into vast, ever-growing halos. Within these halos, the first stars ignited, blazing with a ferocity we can scarcely imagine, forging the first heavy elements in their nuclear hearts. These stars clustered together, drawn by their mutual gravity, forming the first protogalaxies, and those galaxies in turn were pulled toward one another, along invisible filaments of dark matter themselves, dictated by the largest patterns you see on this map. They converged at the great nodes of this cosmic web, creating the colossal superclusters of galaxies that dominate the universe today. Every galaxy, every star, every planet, every living thing, every single structure in the universe owes its existence to these primordial seeds. Look again at the map. That large, cool blue patch is not just a region of slightly colder plasma, it is the ghostly ancestor of a vast cosmic void, an immense region of empty space where galaxies are sparse. And that fiery orange spot beside it is the progenitor of a future supercluster, a place where tens of thousands of galaxies would eventually be born, a bustling metropolis in the cosmic landscape. We are looking at destiny. We are seeing the template for the cosmos, the initial conditions from which the entire 14 billion year story of cosmic evolution unfolded. Without these tiny miraculous imperfections, the universe would have remained a thin, featureless and eternally boring soup of hydrogen and helium. There would be no galaxies, no stars, no planets. There would be no life. There would be no one to build a telescope and look back in time. The fact that we are here able to comprehend our own origin story is written into the very fabric of this ancient light. This map is not just a record of the past, it is the ultimate explanation for our present. It tells us why the universe is not empty, why it is filled with such magnificent and complex structure. It is the reason we exist. And yet, for all that this image reveals, its greatest power may lie in the new questions it forces us to ask, in the deeper mysteries it illuminates just beyond the edge of our understanding. We have read the primary text of our cosmic Rosetta Stone, but we now suspect there are hidden inscriptions written in a fainter, more subtle script. The next great quest in cosmology is to decipher this hidden language. This brings us to the future, to a new generation of cosmic explorers, designed not merely to refine the map we have, but to search for something else entirely, something predicted by our theories but never before seen. They are hunting for a particular kind of twist, a faint spiral pattern, in the polarization of this ancient light. This signature, known to scientists as primordial B-mode polarization, is the holy grail of modern cosmology. Finding it would be like finding a fossil from the first trillionth of a trillionth of a trillionth of a second after the Big Bang. Two monumental efforts are leading this charge. On the ground high in the Chilean mountains, an international collaboration is building CMBS-4, the next-generation cosmic microwave background experiment. It won't be a single telescope, but a vast army of them, an interconnected network of 21 separate instruments, equipped with over 500,000 superconducting detectors, more than all previous CMB experiments combined. Working in concert, they will map the sky with a sensitivity that beggars belief, peering into the microwave background with a clarity that will make even Planck's incredible data look coarse. CMBS-4 is an industrial-scale enterprise for a question of fundamental importance, a brute-force attempt to wring every last drop of information from the universe's oldest light. Its goal is to find the telltale B-mode signature, or prove it is too faint for even this colossal machine to detect. Meanwhile, a different kind of explorer is being prepared for a journey into space. Japan's Lightbird satellite, the light satellite for the study of B-mode polarization and inflation from cosmic background radiation detection, is an instrument of exquisite finesse. While CMBS-4 leverages overwhelming power, Lightbird will rely on the pristine, uninterrupted view from orbit, far above the distorting effects of Earth's atmosphere. For years, it will patiently scan the entire sky, its detectors searching for that elusive twist, that faint ghostly spiral in the light. Together, these two grand projects, one on the ground and one in space, represent our best hope of opening the next window onto the birth of the cosmos. They are not competitors, but collaborators in a single audacious goal. But what would finding this signature actually mean? Why is it so important? The existence of these B-modes is the key prediction of the theory of cosmic inflation. Inflation proposes that in the first fleeting instant of time, the universe underwent a period of violent exponential hyperexpansion, stretching from a size smaller than a proton to something larger than a grapefruit in a fraction of a second. This breathtaking expansion would have been so energetic, so cataclysmic, that it would have shaken the very fabric of space-time itself, generating a storm of gravitational waves, ripples in the geometry of reality. These primordial gravitational waves, born in the universe's first moment, would have then propagated through the expanding cosmos, stretching and squeezing space as they went. As they passed through the hot, dense plasma that emitted the CMB, they would have left a permanent, indelible mark, imprinting a faint swirling pattern onto the polarization of the light. This is the B-mode signal that CMBS-4 and Lightbird are hunting for. If they find it, the consequences will be almost beyond measure. It would be the first direct observational evidence of inflation transforming a brilliant theoretical idea into a confirmed historical fact. It would give us our first tangible glimpse of the physics that operated at energies 1 trillion times higher than anything we can achieve in our most powerful particle accelerators on Earth. We would in essence be using the entire universe as a particle collider. Detecting these primordial gravitational waves would also represent the first evidence of the quantization of gravity, a whisper from the era when the fundamental forces of nature, including gravity, were believed to be unified into a single magnificent superforce. It could open the door to a theory of everything, the ultimate dream of physics. And perhaps most profoundly, it would allow us to peer back beyond the cosmic microwave background, past the wall of fire from the early universe, and see the shadow of the Big Bang itself. We would not be seeing light from that time, but feeling the echo of its tremor, the aftershock of the single most violent event in cosmic history. This is the frontier. The journey that began with an unwanted hiss in a radio horn has led us to the very edge of conceivable knowledge, to the threshold of creation itself. We have travelled from the accidental discovery of a faint glow to the deliberate high-tech hunt for the gravitational echoes of the universe's birth. And if we fail to find this signature, that in its own way would be just as revolutionary, it would mean our leading theory of the universe's first moments is wrong, or at least incomplete, forcing us back to the drawing board, challenging a generation of physicists to dream up new ideas about how our cosmos truly began. Either way, whether through discovery or through profound telling silence, this ancient light still has its most important secrets to share. This 8K reconstruction, as complete and beautiful as it is not an ending. It is a testament, a monument to how far we have come, but it is also a signpost pointing the way toward an even deeper unknown. It is a reminder that the universe is not just a collection of facts to be memorized, but a living, evolving story that we are a part of. We are the universe made manifest a way for the cosmos to know itself, the light that travelled for nearly 14 billion years to reach us, the light that Penzias and Wilson first stumbled upon, the same light that our most advanced satellites have now mapped with such grace and precision, is the light that connects us to our own ultimate origin. It is our shared inheritance, the birthright of every curious mind that has ever looked up at the night sky and wondered, where did all of this come from? The answer we have found was all around us all along, waiting to be seen. And the next chapter of that answer is still out there, encoded in the faintest whispers of light, waiting for us to learn how to listen. The quest continues,